Hello guys, compliments of the season, happy new year in advance. Today we are going to talk about a topic in chemistry, which is atomic structure, and one of the ground breaking topic in chemistry. And if you're new here, please click on the subscribe button and click on the bell beside it to notify you when we drop a new video. And if you are old here, thanks for coming back again. So what do we understand by atomic structure? Firstly, we need to define what is called atom. What is an atom? When I say an atom, what does it mean? All matters are made up of a tiny particles. A tiny particle is called atom. In the days of Dalton, he said atom is the smallest indivisible particle of an element. Anyway, that is also correct as at then, but discoveries has showed that atom is now divisible because we have some subparticles of atom, which is what? Proton, neutron, and electron. So this gives rise to the study of atomic structure, because as small as an atom is, we still have subparticles. So what prompts to the research on what small particles are present in atom is as a result of some certain things that the definition of Dalton couldn't explain why some metals or some materials conduct electricity, why some does not. So that gives rise to the study of atom for the discovery of what? The three more subparticles. So when we talk about atom, the new definition for atom is the smallest particle of an element which take part in chemical reaction. In the days of the atom, we believe atom is the one responsible for the reaction to take place. But anyway, it has been clarified that atom is just only part of the reaction. But the major reason why the reaction takes place is because of the what? Electron in the around the nucleus of an atom. So let's quickly look at the structure of an atom in forms of diagram, then we'll begin to talk more about it. So now, anyway, the structure of an atom after the discovery showcased that atom has a center called nucleus. Then around this nucleus, we have electron moving around the nucleus. The electron is not restricted to a particular part of movement, but we are just putting an imaginary circle or a line just to represent the possible position of electron around the nucleus. So now we assume electron is outside the nucleus. So this is electron. This is electron, and this is what? Nucleus. This nucleus consists of proton, which represented as, and neutron, represented by N. Electron is represented by E minus. It was discovered, electron, proton, and neutron were discovered by different scientists, and their property was also given, because the property of proton says that, let's look at particles, subparticles of atom, and their masses and their charge. So it was discovered that proton has a mass of 1 and charge of +1. Electron has no mass, or let's say, yes, we can say it has no mass because the mass measured is just about 1 all over 1,840. So we can say it has no mass, then, but it has a charge of -1. While neutron has the mass of 1 but no charge at all. So these were the property discovered for the subparticles of atom that was discovered then. So we have more to talk about in atomic structure, as we're going to talk about the number of proton, the number of electron that is likely to be found in the nucleus of an atom. As we arrange elements from hydrogen to calcium and more, but anyway we are restricted to first 20 or first 30 elements. As we arrange them, they are arranged according to their atomic number. And what is atomic number? Atomic number represents the number of protons present in the nucleus. So atomic number is equivalent to number of proton present in the nucleus of an atom. So if this nucleus consists of one proton, definitely the atomic number of that particular atom is going to be 1. So the number of proton determines the atomic number. That is what atomic number is all about. So what I was saying was that elements we arrange according to the atomic number, so which corresponds to the number of proton that is present in the nucleus of an atom. So hydrogen, being the first member of the first 30 elements, has the atomic number of 1, which means it has 1 proton in the nucleus. Now, there is one more explanation about atomic number. The number of proton in the nucleus must always be equal to the number of electrons outside the nucleus if the atom will remain an atom. What do I mean by that? Let's look at an atom. In example, has +2, which means this +2 shows it has 2 proton. Since proton carries positive charge, so we don't have 2 plus. Now it must have 2 electrons outside the nucleus, so that we are going to have -2 plus 2, that will give us 0 charge. But in the other way around, if otherwise, one charge will be greater than the other. Suppose we are having just 1 proton here, and we are having 2 electrons. So definitely we're going to have -2 plus 1, which is going to give us -1. So that shows that this particular atom is not meant to be called atom anymore. It is now called an ion. So an atom must have equal number of electron and proton. The number of proton inside the nucleus must be equal to the number of electron outside the nucleus. So, and at the same time, the number of neutron does not have anything to do with the charge, but it contributes along the line with the number of proton to the mass of the atom. So let's take, for example, if I have like hydrogen, for example, hydrogen has only 1 proton but no neutron in the nucleus. So the mass of hydrogen, of the atomic mass, is to be what? Is to be 1. The atomic mass, or you call it mass number, is 1. Why? Because it has only 1 proton. Suppose it has a neutron, the mass is going to be 2, depending on the number of neutron it has. If it has 2 neutrons in addition to this 1 proton, that means the mass will be 3. But anyway, hydrogen has the mass of 1, which is contributed by the single proton it possesses. Why? Since I have made mention of equivalence in number of proton and electron, so definitely hydrogen will have only 1 electron. So as you move down the first 20 elements, you get more complex atoms that have more than 2, 3, 4, 5, 6, 7 electrons, and so on. So we're still going to talk about how to arrange this electron outside the nucleus, because electrons don't just go out the nucleus or just stays around the nucleus. There is a specified arrangement for electrons around the nucleus. So now let's talk more further about the particles in the nucleus. Now we need to look at, we now understand the concept of atomic number, and we have to understand the concept of mass number as well. When you say mass number happens to be a number that corresponds to the mass of an atom. So, and that has to be the sum of the neutron and proton. The sum of the proton number, which is the atomic number, and the neutron number. So when we talk about mass number is the same thing as atomic number. I will abbreviate atomic number plus number of neutrons. Number of neutrons. And at the same time, I can also say this: atomic number is the same thing as number of electron and also the same thing as number of proton. So they can be used interchangeably. If I know the number of electrons present in an atom, so there is no need to begin to rack my brain for the atomic number or the number of protons. I know they have to be equal if the if the atom still remains an atom. Otherwise, it has become an ion. So now, talking about mass number, we have to add the atomic number with the number of neutrons to give you your mass number of an atom. So now, let's go straight to much more subtopic like isotopy. Isotopy. What does isotopy mean? There are situations whereby we have atoms of the same elements. As I've said earlier, hydrogen will always be hydrogen. Wherever you find hydrogen, it will always be hydrogen. Though we have isotopes of hydrogen, that is where we are moving to now. But hydrogen, looking at it let me use an element that doesn't have an isotope. Let's take a look at aluminium. Aluminium is number 13 as you arrange from first 20 elements. That means it has 13 protons. It has 13 protons. It has 13 protons. So these 13 protons correspond that it has 13 electrons. It has 13 electrons. So now, if I now bring another element, or let's say like elements in like chlorine or thereabouts, chlorine, we have an atom of chlorine that has 35, and atomic number is 17. Anyway, I have to say this. The atomic number of an element is always written at the downside here, and this is the mass number. So the mass number, don't forget, is the sum of atomic number and number of neutrons. So if you want to get the number of neutrons present in this particular atom, you subtract this 17 from 35. It's going to give you the number of neutrons present. And this will be the mass number. Very easy. Now, let's look at the case we're talking about. This is another chlorine atom. Atom of the same element. Atom of the same element. Chlorine and chlorine. They are having the same atomic number but different mass number. Can you imagine? Have we ever wondered why the mass number of chlorine is 35.5? Anyway, we have some other elements with a straightforward, a whole number, atomic number, but in the case of chlorine, we have decimal here. Have you ever wondered why? And some other elements that you might not be familiar with. So now, chlorine has 35 as its mass number here, and we have another atom of chlorine that has 37. But the atomic number is the same. This phenomenon is what we regard to as isotopy. So, and these two, they are isotopes. Chlorine is an isotope because it exhibits isotopy. It showcases isotopy. So when we are meant to define isotopes and isotopy, we have to give it a different definition. We have to clarify that isotopy is the phenomenon whereby atoms of the same element have the same atomic number but different mass number. So now talking about isotopes. Isotopes are atoms that exhibit isotopy, or let's say elements that exhibit isotopy, because chlorine is an element. Hydrogen also exhibits isotopy because we have an hydrogen of this 1, 1. Don't forget, I told you this hydrogen has 1 proton and no neutron. So therefore, the atomic number is equal to the mass number. Then we have hydrogen with 1, 2. This is what we call deuterium. Then we have the one with H, 3, 1. That's a tritium. So this is what we call tritium. And this is deuterium. Yeah, and this is polonium. So these are the isotopes of hydrogen. So that is what isotopy is talking about. That is all isotopy is talking about. But now let's look at how we can calculate, how we can get the value of chlorine's mass number. how is this 35? How do we eventually arrive at this 35.5? So now let's look at it. The percentage abundance, if you have about 100 chlorine atoms, 25% of it are always this, while the 75% remaining will be of this. So meaning if I'm going to work with 100 atoms of chlorine, every 100 atoms of chlorine you always find 25% to be this, and you always find the remaining 75% to be this. So how can we, from this percentage abundance, this one takes 75% and this takes 25%. So from this percentage abundance, you can calculate the mass number of chlorine. So how do we do that? We're going to have 75 over 100 times 25 plus 25 over 100 times 37. So having had this, we are going to make the calculations, and this gives us 9.25, and this gives 26.25. So adding these together, we're going to have 35.5. So this is how we arrive at the mass number of chlorine, which we generally use now. So now, talking about atomic structure and properties of particles in the nucleus and outside the nucleus and their masses and so on, we can stop there, then move to electronic configuration. So electronic configuration of atoms. Electronic configuration of atoms. What do I mean by electronic configuration? Very simple. When you talk about electronic configuration, you're talking about the arrangement of electron in the nucleus of an atom. How do we arrange electron in the nucleus of an atom? That is what is referred to as electronic configuration. How is it arranged? Let's take some explanation that would help us in getting a better understanding about electronic configuration. Let me take it from hydrogen atom. We assume that hydrogen, or we believe that hydrogen atom has one proton. Good, fine, that's a fact. And it has one electron, that's also a fact. But we believe this electron reside just very close to this nucleus, and sometimes they call it orbit, but it's not an orbit, because orbit is a path you must continually maintain, but electron can jump from that particular position to another position. So out of the whole space here, there is a lot of space the electron could occupy. Yes, there is a lot of space electron could occupy or jump to, depending on the amount of energy it received. So how is this discovered? Why? Because when you supply energy to this electron being here, electron choose to be in a shell. We call this shell, or energy levels. Electron choose to be in the lower energy level, which is called the ground state. Ground state. So the ground state happens to be the energy level closer to the nucleus. So electrons choose to be in this ground state because they have no energy in them. So, but in a situation where you supply energy to electrons, they tend to jump to higher and higher orbits depending on the amount of energy supplied. So they jump, and whatever goes up will definitely comes down. It's certain. It's a law of nature. Whatever goes up will definitely comes down. So when you supply energy to them, they jump. Depending on the amount of energy, they jump towards higher orbits. Then when they get to higher orbits, they tend to come down And while coming down, they release an energy in form of light. They release energy in form of light. So this light energy is, if passed through a spectroscope and was analyzed, we see a series of lines that showcases the energy levels in the atom. Let's take it this way. Have you ever wondered why when when you heat up an iron rod in a flame for a long time and you bring it out, you're going to see a kind of color change, or let's say red. It becomes red, it becomes reddish. Why? This is what is taking place. This is what is taking place in the metal. Why? Because the electron from its atom has been given a minimum amount of energy to jump to higher and higher orbit. So while coming back to the ground state, they release that energy in form of light that could be analyzed with a spectroscope. So we have the ground states of energy, and we have more positions, or let's say energy levels. So this happens to be the lowest energy, so we can have more of it around the nucleus. It continues till infinity. So now let's go straight in explaining more about this. Talking about electron arrangements, atoms starting from hydrogen, that means they have smaller number of electrons starting from 1. Helium we have 2, 3, and so on, going to lithium and so on. As we move down the first 20 elements, we go to more complex atoms. So a situation whereby we have atom of about 10 electrons, 20 electrons. How are we going to arrange those electrons around the nucleus, or are they just going to be there? No. So we need to talk about the criteria, or the process, the procedure, the benchmark of the arrangement. What makes the arrangement very easy? So the arrangement of electron around the nucleus is based on 4 quantum numbers. 4 quantum numbers. The 4 quantum numbers. The number 1, we have the principal quantum number. The principal quantum number. So this principal quantum number corresponds to the number of energy levels. We use letters to also represent them. So this ground state can be represented with K, and the next energy level to it will be L, M. It continues. So the principal quantum number corresponds to the energy levels present in the atoms. The number of energy levels present in the atom. And when you talk about energy levels, we are going to look at some that are far away from the nucleus and some that are closer to the nucleus. So, and they correspond to letters like K, L, M, N, O, P, and so on. And they also correspond to numbers. So as this K, we represent 1, 2, 3, 4, 5, 6, so and so on. So they correspond to that. Now, these principal quantum numbers are not just the only energy levels present. They have sub-levels, meaning that if electron is occupying this particular energy level, is occupying the sub-levels in it. In the sub-levels, anyway, let me break it down in this form. In the sub-levels, you have orbitals. Let me take it to the normal life scenario. Okay, let me say in a house. You can stay in a house actually, but where we use stay or where we use sit, you can sit in the house anyway, but where we use sit is in a chair. In a chair, or let's say, okay, you can sit in a house, you can sit in a whole building, you are in a building, but don't forget, in the building you have sitting room. That's like a sub-level. So the building now is corresponding to the principal quantum number, is corresponding to the principal quantum number. So now in the building you have sitting room. So the sitting room happens to be the sub-shell. But inside the sitting room, what are you going to sit on? You're going to sit on the chair. So the chair will now serve as the orbitals. So that is the name that will be assigned to them as far as electronic configuration is concerned. So the whole building, the house, is representing the principal quantum number. Then the subshell, or you call it sub-levels, they are called the subsidiary quantum number, or ZIMUN. Subsidiary quantum number, or you call them ZIMUN. They correspond to the number of subshell, and this subshell could be any of these S, P, D, F. When I say subshell, you are in a building which happens to be the principal quantum number, and in the sitting room, which is a subshell. And sitting room, we have different sizes, as you know. So, and the larger the size, then it can accommodate more chairs. The larger the size of the sitting room, then it can accommodate more chairs. Let's look at it in that perspective. So the chairs of different size, it can accommodate chairs of bigger size, smaller size. So these subsidiary quantum number are SPDF, and these SPDF, they are now the sitting room, and they will have chairs in them. So because this is the first one, it has a limited space. So that means it has only just one orbital. That means a single chair. That means in this S subshell, you have a single chair. Now P, you are going to have 3. Though the quantum number that tells us which the number of orbital present in the subshell is what we call the magnetic quantum number. Magnetic quantum number. And we have the spin quantum number. In order not to cause confusion, what I'm trying to say in essence is that the principal quantum number represents the shell energy level, starting from the lower one, the ground state, to the higher ones. So each energy level we have subshell, which are the what? SPDF. And the subshell, we have a space for electrons to occupy, and those space is what we call orbitals. So this subsidiary quantum number corresponds to the number of subshell. This magnetic quantum number corresponds to and magnetic quantum number range from 0. Okay, range from -1 to 0 to 1. And the spin quantum number is just -half to +half. We're going to get there. Anyway, this will guide us in writing the electronic configuration. So the subsidiary quantum number corresponds to the number of sublevels, and each sublevels we have a space for electrons to occupy, which is called orbitals. So the number of space available is determined by the magnetic quantum number. So the magnetic quantum number tells us that S only have one orbital, and each orbital will have a spin of -half and +half, meaning that 2 electrons can occupy that single orbital, and they will occupy and spin in opposite direction. That is why the spin is what? Is -half to +half. So if this represents an orbital, if this square box represents an orbital, that means this is a single orbital. The magnetic quantum number tells us that S orbital is a single orbital. Then the spin, the type of spin that will present in every single orbital is going to be what? -half to +half, meaning that electron is going to spin in opposite direction while filling the orbitals if there is 2 electrons in it. So each orbital can accommodate 2 electrons spin in opposite direction. So we have -half to +half to give us 0 spin in the orbital. In the orbital, we have 0 spin. So now let's go straight to how we can make use of all these things in writing electronic configuration. Starting from hydrogen, which happens to be the simplest of all. Hydrogen. Hydrogen is making use of the first shell, the first energy level. Don't forget, hydrogen is making use of the first energy level. So therefore, we are going to write 1, and hydrogen is making use of s orbital, s subshell, which has only one single orbital. So meaning we are going to write as 1s. So hydrogen is making use of the first shell, the ground state, and in the ground state, we have a sublevel which is what? S. The subsidiary quantum number s, and this s is only a single orbital which can accommodate 2 electrons. Though hydrogen doesn't have 2 electrons, so hydrogen is filling only 1 into that. So we're going to have 1s1. So which we can represent in form of diagram as this. Now, secondly, we have helium. Helium will be 1s. Helium still maintains the second shell, the first shell I mean. So if you have to write this in a general way, you write it this way. Though we fill it here, but the normal way of filling it is correspond to the orbitals. So now, helium has 2 electrons as they were arranged. I've said earlier, the number of proton is equal to the number of electron. So if I say they are arranged according to the atomic number is the same thing as number of electron. So the number of electron corresponds to the number of proton. So it has 2. Then the orbital diagram is going to be a spin up and down to give us the zero, is our zero spin. Now, why are they meant to spin in opposite direction? There is a rule called Pauli exclusion principle. Pauli exclusion principle. This principle tells us that electron in the same orbital cannot have the same value of all the 4 quantum numbers. Electron in the same orbital cannot have the same value of all the 4 quantum numbers. What does that mean? Look at this electron. Here in hydrogen, it has no partner. Good. Now, going to this helium, the electron here is making use of 1s orbital, good. And the second one is spinning in opposite direction. Why? Because they cannot behave in the same manner. Let me just say it in that way. They cannot behave in the same manner. Electron in the same orbital cannot behave in the same manner, and they don't have the same value of all the 4 quantum numbers. Let's take it from here. One will be minus half, one will be plus half. So let's take it that way. So we move next to lithium. Lithium is going to be 1s, Having filling the first shell always accommodates just 2 electrons. Why? Because it contains only s orbital. This first shell contains only s orbital. So if we have this, it's complete. It has attained its octet configuration. This is duplex configuration. This is what we mean by duplex configuration. The octet configuration is when you have your configuration of complete 8 electrons in your shell. But the ground state can only accommodate 2 electrons because it only has one sublevel, which is the s, and that s has only one orbital that can accommodate 2 electrons. So now, lithium, first orbital is full, then we go to 2s. How do we arrange this? If we have 1s orbital, 2s, 3s, 4s, 5s, 6s. The first orbital does not have p. Why? Because it only contains s orbital. So we have 2p, 3p, 4p, 5p, and 6p. Then we are going to have 3d, 4d, 5d, 6d, then 4f, 5f, 6f. So the electron enters the orbital in this manner. 1s first. Once the 1s orbital is full, we go to 2s. Once the 2s orbital is full, we go to 2p, then 3s, then 3p, 4s, just like that. So that is why the next one we have to move to. That means we are going to the second shell. And the second shell we have s orbital. Good. So we have to make use of the s orbital for the second shell first. Then when we are through with that, we go to the what? The p. If the s of the second shell is full, then we go to p, since p is the next subsidiary quantum number. So we have 2s1. So that showcases that what? Don't forget s has only one orbital, but p can have 3 orbitals. P can have 3 orbitals, meaning it can accommodate 6 electrons as 2, 2, 2 each. Then D has 5 orbitals, which can accommodate 10 electrons. That's 5 orbitals. Then F has 7 orbitals, which can accommodate 14 electrons. So those are the values of orbitals, number of orbitals present in the subshell, and the number of electrons it will accommodate. So now let's write it up to probably the 10th member of the, or let's say the 8th. So lithium, we have beryllium, 1s2, 2s2. So we have this. Now, according to the octet rule states that after the first shell is completely filled with electron, that means that's obtained the two-plate configuration, every other shell must obtain 8. Anyway, initially the number of electrons that is likely to be found in the shell is given by this. But by following the octet rule, every other shell apart from the first shell, the ground state, must take 8 electrons as the highest number of electrons they can accommodate. Every principal quantum number. Each principal quantum number must not accommodate more than 8. So once the principal quantum number is getting to 8, apart from this, which is 2, once this is getting to 8, you have to move to this. Once this is getting to 8, you have to move to this. That is how it is. So now we have beryllium, boron, 1s2, 2s2. The next one will be 2p, as we have said earlier, 2p1. So we are going to have this. Good. So beryllium, boron, we have carbon, which is 1s2, 2s2, and 2p2. Anyway, this is what I want to drive out. You might expect me to fill it here, but no, I'm filling it here. Yes, because there is a rule that states that electron must occupy the orbital singly first before pairing takes place, and that is called Ohm's rule. Ohm's rule of maximum multiplicity. Multiplicity states that electron occupies the orbital singly first before pairing takes place. And anyway, we have been making use of a rule that I have not mentioned so far. I mentioned Pauli exclusion principle, which tells us why electrons have to spin in opposite direction, and which is supported a bit by the spin quantum number. Then we have the Ohm's rule that tells us that electron occupies the orbital singly first before pairing takes place. So we also have another rule that is called the Afal's principle. Afal's principle. This states that in building up of an atom, electron occupies the orbital with lower energy first. In building up of an atom, electron will occupy the orbital with lower energy first. So that is why you have to fill in 1s. That is why the arrangement 1s, 2s, 2p, 3s comes in, because going to the energy levels, 1 has the lowest, 2 lower to that of 3. So electron must occupy the energy levels of lower, must occupy the lower energy levels firstly before going to the higher ones. So that is why you can see 1s, 2s, 2p. P doesn't have d, so it stops as p. Then we have 3s, we're going to have 3p, then 4s, 4s, 4p, 5s. So it continues that way. That is what Alva's principle talks about. So now let's look at some cunning questions that normally comes out from electronic configuration of atom for JAMB and WAEC students. Now a question comes thus that anyway we can write the electronic configuration in another form like this. We have 1, here we have 2, here we have 2, 1, here we have 2, 2, here we have 2. Anyway, we are joining these together because this is 1 orbital, this is 2 and 2, this is 2 subshell, and this is 2 subshell, so we can add this together. Then we have 2, 3. So as it is now, we can have 2, which is the first shell that must not take more than 2. So the next one can take as up to 8. All other ones can take 8. So once this is up to 8, you have to move to the next one. So now there is a question that comes in JAMB like I have a question that says which this configuration is not along with so rule. I have this. So the question says the configuration here is not in line with a particular rule. So we have options like Gauss principle, or the exclusion principle, on rule of maximum multiplicity, and so on. So the best answer for this is, as you can see, according to what I'm saying here, the electron is not occupying the orbital singly before the pair. So it has paired immediately and leaving these orbitals empty. So therefore, it does not obey on rule. The correct answer to that is it doesn't obey on rule. So on rule is being violated as far as that is concerned. So let's look at another one like this. This electronic configuration does not obey Gauss principle. Why? Because it was said that electron occupies the orbital with lower energy first before moving to the ones of higher energy. So, and this one with lower energy is yet to be filled up. So while filling into the higher energy, so that is what those rules are talking about. And sometimes you might be given an electronic configuration to write, to name the element. So let's take a look at this. We are meant to name this element now. How do we name it? Firstly, I know this is first shell. Second shell, I can add that. That will give me 8. The third shell, I have 1. So this is the configuration. 2, first shell. On the second shell, I add it. That's 8. Then third shell, I have just 1. So now, how do we name this particular element? So the counting, this is 2 plus 8, that's 10 plus 1, that is 11. So counting from the first 20 elements to the number 11, that happens to be sodium. So you can just say the electron configuration here is for sodium, Na. So these are various questions that might come your way while writing exams to make use of them. And this particular aspect of chemistry is one that you have to understand very, very well because it forms the basis of every other aspect of chemistry. So we can also solve so much more questions as far as this is concerned. Probably in the next video, we pick 1 or 2 questions to solve on this. Majorly, those questions that comes out of here, they are always mostly in objective. So thanks for watching. Please subscribe to our YouTube channel. It's free. Thank you.